Velocity time graphs don't only tell us about the velocity and the time, they also tell us about the acceleration and the total distance travelled. On the x-axis we put time, and on the y-axis we put velocity or speed. I won't go into the difference between velocity and speed in this video, but for the context of this video we can consider velocity and speed to be the same thing. They're not quite, and if you really want to know about the difference between them, then why not subscribe to my channel and watch my video on vectors, which will explain a lot more. From a distance time graph you can determine the speed from the gradient of the graph. I'll leave a link to my video on distance time graphs in the description along with the other one. With a velocity time graph, the gradient gives us acceleration. Let's take a look at a simple car journey. The car starts with a velocity of 0. Then over 10 seconds it speeds up to 15 meters per second. And then for the following 40 seconds it remains at the constant speed of 15 meters per second. And then in the last 10 seconds it slows back down to 0 again. Notice the horizontal line between 10 and 50 seconds. This means the car's travelling at a constant speed. With a distance time graph though, a horizontal line means the object is stationary. This catches an awful lot of students out, so do check which graph you're looking at, distance time or velocity time. Now let's take a look at acceleration. I've already pointed out that acceleration can be found from the gradient of the graph. So let's look at the gradient of this graph in the first 10 seconds. The gradient is the change in y over the change in x. The change in y is 15 meters per second. The change in x is 10 seconds. 15 divided by 10 gives us 1.5 meters per second squared. There are two things to note here. First of all, the units. Because we take speed and divide it by time, we're doing meters per second divided by seconds. So the units for acceleration are meters per second, which we can also write as meters per second squared, which is what you will see most of the time. The second thing to note is the gradient that gave us our acceleration is the change in velocity over the time taken. That is our equation for acceleration. Acceleration equals change in velocity over time taken. In physics and maths, we like to use the Greek symbol delta to represent change. You'll see that quite a lot. Delta V, therefore, is change in velocity. We could also write the change in velocity as V minus U, where V is the final velocity and U is the initial velocity. So V minus U just gives us the change in velocity. So to summarise so far, acceleration is found from the gradient of a velocity time graph. Acceleration can also be found from the equation change in velocity over time taken. And the units for acceleration are meters per second squared. Let's head back to our car journey. We've calculated the acceleration to be 1.5 meters per second squared for the first 10 seconds. The car is then travelling at a constant velocity of 15 meters per second for the next 40 seconds. So what's happening in the last 10 seconds? Well, the car is slowing down. We can see that from the negative gradient. If the gradient is negative, the acceleration must be negative. We sometimes call a negative acceleration a deceleration. Let's calculate the acceleration. So the acceleration is change in velocity over time taken. The change in velocity is minus 15 meters per second, and the time taken is 10 seconds. Therefore, the acceleration is minus 1.5 meters per second squared. Now, if I was to ask you about the deceleration, it would be okay to miss out the minus sign and just say, well, it's decelerating at 1.5 meters per second squared. But if you're asked about the acceleration, then it's important that you include the minus sign. So it's minus 1.5 meters per second squared. The minus sign is really important. It's the only indication we have that the car is slowing down and not speeding up. Of course, a minus acceleration is exactly the same as a deceleration. Before I show you how to calculate the distance travelled from a velocity time graph, can I point you in the direction of my website, and I'll leave a link to it in the description below. On there you'll find lots of free resources, including questions and answers to go with this and every other video. I also offer one-to-one lessons and tuition in small groups. There's more details on the website, but I do try and keep the prices as affordable as possible. Do also like, subscribe and comment. I love to read the comments. That'll help me grow as a channel and provide more and more free resources. So how far does our car travel during the journey? Well, let's take a look at the middle 40 seconds first, where it travels at 15 meters per second. Distance is speed times time. So we take our speed of 15 times our time of 40 seconds and we get 600 meters. Now you may have noticed that this calculation is exactly the same as calculating the area under the graph for this time. Along the bottom we have 40, up the side we have 15, so our rectangle has an area of 600. That is exactly how we do calculate the distance travelled from a velocity time graph. We calculate the area underneath it. So how far does the car travel in the first 10 seconds? Well, here we've got a triangle. And the area of a triangle is half base times height. So it's half times 10 times 15. So in the first 10 seconds, the car travels 75 meters. Similarly, in the last 10 seconds, we've also got a triangle. So we can calculate the area there as also being 75 meters. For the total distance travelled, we add these three areas together. 75, add 600, add 75. And we get 750 meters. The total distance travelled during the journey. Now, why didn't you watch this? Have a look. Have a look at this. Watch this.